All right, 4.8, application problems, trigonometry. There are two learning objectives I want to pull out of this section, and that is systems, that's the good old algebra stuff, and with trigonometry. And now we have simple harmonic motion, which is just physics applications of trigonometric functions. First one is the systems problem. Go ahead and draw at least the triangle here and the bigger triangle, because you're going to need that for reference. And you'll just reference back to the textbook as far as what it actually talks about. Alright, you can read the pause the video and read the statement, but we have the 200, 53, 35, it's all marked up. We need to find the height S of the smokestack. That's just this distance here. So I'm going to set up my two equations and solve, and you're going to see that this is referencing systems. Alright, so the first one I'm going to use, by the way, we assume this is perpendicular if it's a building, otherwise you'll be told if it's not perpendicular. So I'm going to use the tangent ratio. And this is equal to the A over the 200. And I'm going to go ahead and solve this for A. So A is equal to 200 times tan 53. Now that's helpful, but it doesn't help us directly to find S. So we're going to have to do another equation to find S. And I'm going to switch colors for that. So this is tan, tan of the, oh, I said 53 there. It's actually, I apologize. It's not 53, it's 35, which I'm sure you probably realized that was a mistake, but I caught it. 35 degrees is the small angle. Common mistake though, so you just saw me go through it. Tan 53 on the other hand is the bigger triangle, and that goes with the opposite, and the opposite is A plus S divided by the adjacent 200. Now we just need to solve for the A because they're equal to each other. So I'm going to solve this equation for A. That is, I'm going to multiply both sides by 200 and subtract S. Notice that's equal to A, and the other one's equal to A. That means that I can set these two equations equal to each other, and I'm going to do that here, since they're both equal to A. My personal preference is to, that's minus an S, my personal preference is to go ahead and let me shrink this down. Is to go ahead and solve for S, then type it in the calculator. I'm going to check my work real fast to make sure I've done it correctly. Looks pretty good. So S, if I add S to both sides and subtract 200 tan 35, then I get this, 200 tan 53 minus 200 tan 35. Now, we could manipulate this equation, but it essentially comes down to that. So now I'm just going to pull up my calculator, make sure I'm in degree mode. Move this up. Then I just type in 200 tan 53 minus 200 tan 35. 125.36. Fortunately, this is directly out of the textbook, so we can check our answer. 125.4 is what they got. So yes, 125.4. Awesome. That's one with systems. Just want to emphasize, go back to the learning objective. We got to solve application problems of trigonometric functions with systems. As you can see, we have two equations from this problem. Two equations, two variables, but we're all only looking for S as far as the answer. So we just set up our equation with our two equations becoming one. All right. The next concept is simple harmonic motion. Some of you may have seen this in physics, but it just means something is moving in a very harmonic way, or going back and forth, just like the sine wave. The best way to talk about this is with a spring, or the first way we can talk about it. Notice we can call this 0 if that's the resting point, and then it has a negative displacement if it goes, apparently they're calling down as negative and up as positive. If you think of the spring going back and forth, you can think of that as being a trig function or a cosine function. So for now, we're just going to do the basics of this in class. Next time, we will do some more complicated simple harmonic motion problems. But for right now, let's go ahead and define what simple harmonic motion is all about. Go ahead and write these two equations in your notes. We need D is equal to A. Just want to say it out as I write it. Sine omega t. Notice omega is in the place of the B. This is still the angular velocity, and that tells us that our period is equal to 2 pi divided by b, but this b in this case is omega. It's just because of application problems and a The omega is referencing the angular velocity. A is still the amplitude, so I don't really need to write that out. But there is a new concept here, and that's we've talked about this, but this is the frequency. Notice the frequency is the reciprocal of the period. So the frequency is equal to omega divided by 2 pi. But we've been doing this quite a bit with graphing trig functions, so this should be pretty easy to see. Once again, we're just using omega because we're talking about a physics application. Cosine, same deal. All right, so let's go back to that spring problem. Go ahead and draw this spring in your notes, and let's talk about when the period is 4 seconds. The question is, what is the frequency of the harmonic motion? We're going to do this in seconds. Now you saw from before that the frequency is the reciprocal of the period. So this is angular velocity divided by 2 pi. But it tells us that the period, actually we don't need this one, the period is 4 seconds, so the reciprocal of that should be our frequency. So it's 1 divided by 4. Now frequency is asking for cycles per second, and period is the number of seconds per cycle. So obviously they're reciprocals of each other. This is cycles per second. If I were looking for an equation for this, note that the displacement is 10 values. So as far as being cosine or sine, it all depends on where you actually start this ball on the spring. We're going to call it 0, and we're going to say going positive. Notice if we start at 0 going positive, that would be the sine wave. Starting at 0, going positive, that would be sine. So we're going to use the sine function, remembering that the y is equal to a sine omega d, or excuse me, omega x. And we need to find omega. Well, we have the frequency formula here, so we could use that, or we could use the period. Notice that the period is 4, and our formula for the period is 2 pi divided by omega. We need to solve for omega by multiplying both sides by omega and dividing by 4, so omega is equal to pi over 2. The amplitude is the maximum displacement away from the equilibrium point. The equilibrium point is the same thing as the oscillating axis. So that's 10. So A is equal to 10. That means that the equation is simply y equals 10 sine pi over 2x. Now the textbook talks about this problem slightly differently. They decided to, no wait, they did do it with sine. So same equation. And I believe that is it. No, I lied. I want to do one more problem. Given the equation for the simple harmonic motion, we're going to do this algebraically and graphically. We're going to find the maximum displacement, the frequency, the value of d when t equals 4, and the least positive value of t when it's d. A lot of stuff going on here. Now, maximum displacement is the same thing as the amplitude. So, done. This is A. Maximum displacement is 6. That means away from the oscillating axis. So how far off the oscillating axis is this cosine function? The frequency is the reciprocal of the period, and it's omega divided by 2 pi. This is our frequency. Omega is in the place of the B spot, so it is 3 pi divided by 4 divided by 2 pi. Notice the pi's cancel. We've got 3 divided by 4 divided by 2. You can remember properties of fractions to know that this is 1 divided by 2, which becomes 3 divided by 8. 3 divided by 8. And that is cycles per unit of time, whatever unit of time that is. And it doesn't tell you what unit it is, so you just got to write it out that way. That's the frequency. Now let's get into part, by the way, this was part B. Let's get into part C. Part C is asking for the value of d when t equals 4. This is a plug and chug situation, so we have d equals 6 times cosine 3 pi times 4 divided by 4. This is something you can do from the unit circle. Notice the 4's cancel. We have 6 cosine 3 pi. If I'm using the unit circle, notice that we have 3 pi going like this. Cosine is negative 1. And this is 6, that means the displacement is negative 6. So if this were an oscillating spring of some sort, if I were going left-right, it would be left negative 6 all the way to the far left at 3 pi. All right, the last one is the least positive value of t for which d equals 0. That means we need to plug in, if we're doing this algebraically, we would plug in 0 for d. So that would be 0 equal to 6 cosine 3 pi divided by 4. This is x. If I were to divide by 6, I get cosine 3 pi divided by 4x. And we're looking for what, let's see for a second. Now we're finding the angle what angle, because that's where the variable is, goes with cosine of 0. That's the same thing as saying this. 3 pi over 4 times x equal to the arc cosine or inverse cosine of x. Remembering that inverse cosine has a range of 0 to pi. So when is it equal to, excuse me, this should have been 0. When is it equal to 0? Well, cosine is 0 at pi over 2. That means the first one, because we're looking for the least value, it's 3 pi over 4 times x equal to that. That means we just need to solve for x by multiplying both sides by the reciprocal of 3 pi over 4. This becomes pi over 2 times 4 over 3 pi. Pi's cancel, 4 cancels with that, becomes a 2, it's 2/3. Alright, so it says the least positive value of t, the time for which d is equal to 0, that time occurs right there. Graphically, I think because of the time of the video, I'd like for you to go ahead and try to do each of these things with a graphing calculator. If you don't have one, do one in class. That's it.